In the last module, we talked about units. In this module, I want to compare and contrast a dimension with units. Now, units are arbitrary, meaning that we can choose any units we would like for our convenience. If we want to work in meters or feet or furlongs, we can choose that. Dimension is not arbitrary. A dimension of an object is absolute. It is an intrinsic characteristic Okay, having problems with my writing here. Characteristic of the object. Okay, so in the first semester of this course, when we study mechanics, all objects will only have a combination of three possible dimensions. There is length, which we can give that a symbol of capital L, time, which I'll call capital T, or mass, which I'll call here capital M. Now, we might have many different units for this. Length could be a meter or a foot. Time could be a second, or a year, or anything else. I'm just giving some examples. Mass might be a kilogram. It might be a gram. We might measure something in terms of the mass of the electron. There are many different units we might be able to use for something that has a mass, but that something is still just a mass. The mass is its dimension, and these are all the different units in which we might represent that dimension. So there's a couple rules on how dimensions work in our algebra that we have to keep track of. And this is called dimensional analysis. And dimensional analysis is also a tool that you can use when you solve problems. As you apply these rules, if you find that your solution violates the rules of dimensional analysis, you know you've made a mistake and you have to go back and check your work. And so this becomes a helpful tool to get the right answer. So rule one. Rule one is when you add, and when I mean add or subtract. But when you add items must have the same dimension. You cannot add or subtract items with different dimensions. And by the same token, then, both sides of an equation must have the same dimension. So you have 2 feet plus 3 feet equal to 5 feet. Each object has the same dimension, which in this case is length, and both sides of the equation have the same dimension, which is feet. Okay, so that's the first rule. The second rule is that for multiplication, dimensions simply multiply. So, for example, if I have an object with a height, a square here with a height and a width, and I want to know what is its area, well, the area is equal to the height times the width. So let's say the height is 4 feet, 4 feet, and the width is 5 feet. Then the result is 4 times 5, which is 20, and the feet multiply, so 20 feet squared. And so that's an example. Let's just do one more. And so one equation that you've probably seen before is that distance that an object travels, if it's traveling at a constant velocity, is velocity times time. And so if I just look at the units, then look at the dimensions, the distance has a dimension of length. The velocity has a dimension of length per time, and time has a dimension of time. And so you can see if I multiply my dimensions together, the times cancel, and I get length. Let's see. I get length on both sides of the equation. And so if you have an equation, for example, if you had said my distance is equal to my velocity times times squared, you could see right away that you're going to get the wrong answer, because this is a length per time times time squared gives me a length times a time, which is not the same as the length, and so this cannot possibly be right. And so this is using dimensional analysis to be able to solve your problems. Okay, so there's one more rule for dimensional analysis. And so here's rule 3, which is arguments of trig and exponent functions must be dimensionless. So they cannot have any dimension. So if I have cosine theta, it has no dimension. This must be dimensionless. And that's important because, as you know, angles are often measured in degrees or measured in radians, but a degree is not a dimension. Neither is radian. They're different ways of measuring angles, and we use them as units. But an angle itself is not a dimension. Okay, and so then again, if I have, say, 10 to the x, where here x isn't the exponent, x is dimensionless. Okay, so let's use these to do an example. Let's say I have the following equation. So let's I have x is equal to alpha t squared plus beta t cubed plus c times sine of omega t. X has a dimension of length. T has a dimension of time. So what are then the dimensions of alpha, beta, capital C, and omega? Okay. Well, I know that this x is a length, so this has to be a length. And I know that objects on either side of an equation have to have the same dimension, and objects added together have to have the same dimension. So this whole thing here must be a length. This whole thing must be a length, and this whole thing must have a dimension of length. Okay. So let's take the first one. I know that so this alpha t squared must be a length. Now how I would do this is I would say, okay, so this is equal to the dimension of alpha, which I'll put in parentheses, which is unknown. I don't know what that is. And so then I need the dimension of the t squared, and it's a time. Since the unit of the result, if t is squared, is t times t, so you multiply the dimensions together. So the dimension of that is t squared. And so these two must multiply together to give me L. And the solution to that is then L over t squared. And that is how both of these sides gives me the units of length. So the units of alpha then is length over t squared. So now let's take the second one, where I have beta t cubed. This also must have a dimension of length, and that's equal to whatever the dimension of beta is. The units of t cubed is time cubed, and so the beta must multiply by t cubed to give me length, so that's length over t cubed, units of beta, the dimension of beta, length over time cubed. Okay, so now let's look at the last one, where we have c sine of omega t. Okay, the omega t has to be dimensionless, we know that. And sine is just of a dimensionless number is also dimensionless. So this entire sine omega t is dimensionless. So for this to have units of length, then c times a dimensionless number is units of length. So that tells us right away that the dimension of c must be length. Okay. And so we also know then that, space here, that omega t must be dimensionless. Well, omega is what we're trying to find. T has dimensions of time, and for this to be dimensionless, omega must have dimensions of 1 over time, so that the result has no dimension at all. And so the dimension of omega is 1 over time. So these rules, the first rule, that when you add items, they must have the same dimension, and both sides of an equation must have the same dimension. When you multiply, the dimensions themselves multiply, and arguments of trig functions And exponents must be dimensionless, can help you determine the dimensions of unknowns in your equations, and then be used to be able to check that you have the right answer by following those rules. And that's the end of this module.